one in certain regimes, so that there's this duality. For example, in the pre-training or fine-tuning setup, I think that I think thinking about in a pre-training or fine-tuning setup, thinking about kernels.
In the fine-tuning.
In a fine-tuning setup, I think thinking about kernels, even plugging in a learned kernel. Maybe you derive something for a fixed kernel, but then you plug in the properties of a learned kernel and see if that holds. So that sort of mixed kind of some theory, but you plug in measured quantities might be useful. But I think that fully doing a derivation from first principles for feature learning, for example, these strongly interacting limits I mentioned, I think is challenging. I think from a physics perspective, it's usually, so one of the goals is to kind of have effective theories. So you don't want to have the full, number of weights, number of parameters set of variables in your theoretical description. You want to reduce, you usually define new sets of variables when you want to kind of talk about something at a higher level. So it's possible that with some combination of, I think, insight about the structure of data and studying those feature learning limits, you could derive reduced sets of basically coupled equations that you could solve. But I think it's challenging to know what is universal or general about that and what is very dependent on that particular setup. So I think it's pretty challenging.
Well, let's thank Yasmin again. So next we have Sasha Rush from Cornell in Hugging Face. What I really like about Sasha is that he both kind of blends the endless curiosity of a scientist, but also can really get things to work and has worked with training really large-scale models. And I actually don't know which combination of those he's going to tell us about today, but either way, I think it's going to be really interesting. So let's welcome Sasha.
Thanks, Jacob. Yeah, so today I'm going to try to engage with some of the theory side of this workshop. I have exactly the opposite disclaimer of Yasmin in that I'm a natural language processing researcher, so the flaws come with that and also the positives. And I'm going to engage with the same topic of neural scaling laws. So I'm going to go through a lot of the same material, but luckily we used almost identical clip art, so it'll work really well in that structure. So today I'm going to present work that was done mainly by Nicholas Moyninghoff. This was work kind of with Hugging Face and a bunch of other folks. It's called Scaling Data Constrained Language Models. We just put it up in the archive about a month ago, so it's relatively recent work. I'd love to hear any comments or questions you may have about it. Cool, so let's talk about scaling laws. So again, I'm kind of coming at this from a more practical point of view. I'm kind of interested in what sort of real world questions we have when building large language models that we need to worry about and how scaling laws can help us answer those questions. So specifically throughout the talk, we're going to have three terms. We're going to have model size, training data, and training compute. I'm going to be entirely focused on training large language models. So that will be the kind of main aspect of the talk. And because they're transformers, there's going to be a coefficient there, alpha, that's well known. We can kind of ignore it throughout the talk, but in practice, it's something like 6. So given our model size, given our training data, we can get our training compute. Different models in NLP have kind of changed these coefficients in different ways, leading to different numbers of training compute. We're going to measure model size in number of parameters, training data in number of tokens, and training compute in floating point operations. So a model like BERT from 2018, which was absolutely revolutionary from the NLP perspective, had about 109 million parameters, 250 billion training tokens, and took 1.6 e to the 20th compute flops. Sorry. And so that's about 64 TPUs over about 4 days at that period of time. Since that point, models have gone in parameter size to about 540 billion. tokens have gone to trillions, and flops have gone much, much larger. This is about the point where companies stopped reporting these numbers. So I could give you the rumors for where we are now, but this is the kind of last hard numbers I feel kind of confident putting in a slide. So in general, this just describes the relationship between these values. We have a kind of multiplicative relationship between model size and tokens, leading to a number of flops. So given this scenario, there are kind of two high-level questions you might want to ask. So imagine you're an executive at, say, Anthropic, and you need to train a big model. You might ask, what will the value of kind of using more flops be? If I increase the number of tokens, how much return is that going to actually give me? Is this worth it? The other question you might ask is one of allocation. And this is slightly different than the last talk. This looks into what's the right balance between increasing tokens and increasing number of parameters that you might want to strike. We know that increasing both of these can give us better loss, but actually determining what the ratio should be is pretty important in practice. If you get it wrong, it could lead to wasted flops. These are the kind of graphs we saw from the last talk. These represent the kind of scaling law properties that show that unbottlenecked by other properties of the system, increasing both model size, training data, and also compute leads to this power law relationship. So you can tell it's a power law because both the axes here are log scale, and we get roughly a linear-like output of our underlying loss. So throughout the talk, I'll just use test loss as a proxy for how good our large language model is. At the end of the talk, I'll engage a bit more with actual accuracy of these models in practice. But the main kind of idea here is that putting in more compute helps, and it helps for both of these quantities, model size and training data. When talking about allocation, I'm mostly going to utilize the terms and graphs from this paper, Chinchilla. Chinchilla provides kind of concrete details extrapolated from a large set of empirical experiments that try to predict how we should allocate between adding more parameters and adding more tokens. So this will be the main kind of graph that we'll utilize throughout the talk. On the x-axis, we have training data in number of tokens. On the y-axis, we have model size. And the labels represent the amount of compute these represent. These four models shown here are four different models and what they decided on this allocation. The Chinchilla paper argues that these models made incorrect allocation choices for the number of flops they utilized and showed that if you utilize those flops instead with an equal balance between model size and training data, you would yield what they call a compute optimal language model. So taking into account the cost of the flops, we're deciding to allocate it to a smaller number of parameters, but more tokens. And here we get a model that exceeds 1 trillion tokens and has kind of led to future models using more and more tokens for these systems. So this will be kind of the main inspiration for this talk itself. And this graph represents kind of how we're thinking about this problem and the questions we're interested in answering. We can write this down with a formula. This formula gives us an estimate of the loss that we'll achieve based on the model size and the training data. So assuming kind of other hyperparameters are kind of fixed or kind of optimized for, we're interested in estimating what our loss will be when we vary these two quantities. So throughout the talk, we'll use n to represent model size and d to represent the number of tokens. And this will give us a functional form that represents the following power law. So we're interested in estimating L, taking into account model size n, data d, and these 5 terms that we're going to fit to a set of empirical experiments. In the Chinchilla paper, they give a rough kind of sense of what these 3 terms represent. So E is kind of a lower bound. That's the true loss of language, the true entropy of language. We can't do better than that. The first term is obviously entirely in terms of the model size itself, represents roughly the types of models that we might be able to learn. The second term represents the fact that we only see a finite number of tokens, and therefore we're kind of bound in how much we can learn about the underlying system. You can think about it that way, or you can think about it as just extrapolating from a lot of experiments and trying to decide how you should actually train your model. When you fit these constants on real experiments, you get that alpha is roughly equal to beta, which explains the equal scaling in the previous slide. Yeah.
You mean, I mean, in the Chinchilla paper, there was some difference. Are you saying now it's actually roughly the same?
This is just describing the Chinchilla paper. I think
Okay.
I think maybe I just mean it in I don't mean in any deep sense, just in that
Roughly, yeah,
Roughly,
that's correct.
Yeah. Maybe more equal than previously had been noted. Great.
One more question.
Yeah.
Is it possible that E here is not the true entropy of the language itself, but it is the limit of what can be learned using the architecture? Like if we change the architecture and like try different type of networks, it's possible that we get to a much lower loss. Like even in the case of infinite resources, is it possible that it will never actually get to the true entropy of the language?
So my understanding is that's what the first term represents. So this first term here represents the fact that your model might not be able to achieve that, whereas the last term really does represent the true entropy of language.
No, the interpretation, that's an interpretation.
It's an interpretation. Yeah.
He's making the point that maybe transformers will never get to the true entropy, regardless of scaling.
Yeah, that sounds right to me. Let's see. I'm mostly reciting how they talk about this in section C of their paper. Yeah, but yeah, it's possible in practice. Yeah.
Yeah, I think that's fair. Yeah.
Okay.
You might talk about it later, but in practice, there's been some work later where people scale data, right, and not scale model size accordingly, and that works well. And whether from a practical perspective, that's how you view that.
Yeah, it's a really good point. So this is somewhat orthogonal to the point of this work, but I think it's actually arguably the most important conclusion that's come out of this, which is that notably the llama models make a kind of conscious decision to scale data more than compute. So roughly that means they end up in this region of the graph. And the argument they give is that inference time, when you actually use the model downstream, is more important than actually compute optimality. So therefore, it's worth getting a worse model, making a bad allocation because of some downstream constraint. Now, I think that is critical in the sense of like when you make these decisions, but it's a purposeful decision to solve a kind of different optimization problem. Yeah, we'll talk about that a little bit more. Cool. Yeah, and just to give you a sense of the scale, Llama 2 is at 2 trillion parameters, so it's roughly around there. But with only 70 billion parameters, so around there. Okay, so given this background, I want to talk about a kind of unique and counterintuitive problem, which is that, well, we're running out of data. And I think this is just a fascinating problem for me and kind of just thinking about how kind of crazy these models are. So this is from a paper that graphs kind of estimates of the amount of tokens available and estimations of when we will actually run out of data itself. So there are 2 lines plotted here. One line kind of makes an estimate of scaling based on the actual models people are building. And the other line makes an estimate based on the increase in compute just from NVIDIA producing more flops for a given price. And I think there are 2 things that are interesting about this graph. One is you can't totally see it here, but there's a kind of very wide variance So it's kind of unclear exactly when this will come about or actually how much data there really is. But the other thing that's interesting is that the amount of data is not really growing at a very fast rate when you consider these scales. So it's not like if you just kind of continue producing tokens, it's going to catch up. There is just kind of a large pool of data. It's increasing at a relatively slow rate, whereas the kind of actual compute is doubling in such a way that it's going to need more data if you believe and follow out these laws. This is a little bit abstract, so we can be a little bit more practical. So some of the estimates of kind of, let's call these like Fermi estimations of given quantities are that if you take kind of high quality books that are available kind of in an open source way, there are about 1 trillion tokens. Oh, sorry, yeah, 1.6 trillion. If you take all the academic papers, that's about 1 trillion tokens. Other sources like Wikipedia are extremely high quality, but they're actually much fewer tokens than you might imagine. And so if you think about these in terms of the scales people are reaching, there aren't that many more orders of magnitude available. Yeah.
It's not really necessarily relevant to your topic, but there's this talk yesterday night about synthetic data.
Mm-hmm.
It seems to be created and done better for the summarization.
Yeah.
So synthetic data is something one can do.
Mm-hmm.
Does that even go into the whole analysis in this field?
I would love to hear Yejin talk about it more, but my understanding is that there's nowhere near kind of evidence that synthetic data can kind of solve this kind of problem. That for like specific tasks, you can construct things in a particular way, but we certainly haven't seen anyone create like orders of magnitude more synthetic text. I want to distinguish that from text generated from already good models. That seems to be effective at training smaller models, but I haven't seen anything where you kind of like actually increase the order of magnitude by generation. But if Yejin's in the room, I'd love to hear if you agree.
Yeah, I've only seen successful cases with the task-specific scenarios. Who knows what some other crazy people with a lot of compute may be able to pursue, but yeah, I think that's yet to be seen.
That's great. I'm gonna get that tattooed on my arm. Who knows what crazy people with lots of compute will be able to do? Yeah.
Yeah, so maybe I want to argue a bit against the data constrained thing, mainly thinking about like distillation using chain of thought or other kind of like basically if you can do anything at inference time to make your model smarter than it would be by default, then this gives you a source of synthetic data because you can kind of get that model to do things and then distill down to the base model. So it seems like this should be a pretty ready source of synthetic data. And there's like some empirical work saying that this, or like showing that this does improve model performance.
Yeah, so actually, let's have this conversation. I think I'm not gonna use the whole hour. I'd love to talk about this more. I think that this talk's gonna be relatively empirical on this one specific thing. So I wanna talk about these other ideas, because that is kind of where I wanna get to. But I wanna argue kind of even within my constraints what we can learn. Yeah, Dee.
It's basically on this page. I'm also kind of against the idea of data constraint because for all the data we are talking about here, this is online data. And we know that only a specific population get access to internet. So we are talking about like a constraint in the way that online data is limited. But your next slide is like, if we think about like a real world and a lot of other populations who are not represented on internet, who don't have access to internet, and also other modalities, that seems to open a lot of space for potential data enrichment.
So let's do the following. Let's have this conversation. I'm going to save time at the end to talk about it. I want to engage with the kind of physics asymptotic mindset just for the talk. So assuming you buy the scaling law stuff, I want to kind of play through this idea. And then we can talk about what to do about it. Okay? Cool. Any other questions about these first things? Great. Okay, so let me just also mention that there's a lot of code, a surprising amount of code. There's about 14 trillion tokens on GitHub. A lot of evidence that the code can actually be used even in regular language models that are mostly natural language. That's a good thing. The bad thing is that if you want to train a model for a specific language, things get much worse. So this project originated because some of the researchers were training a Finnish-specific language model. This was about where they were able to collect about 38 billion tokens. So now we're several orders of magnitude less. And you might argue that why is it necessary to create a giant language model for every language? But I think people in Finland want to do this. It's very important. And so I think whether or not you agree with that, it is something people are thinking about. Okay, great. So let's save these questions for the end. I do want to get back to them. Cool. This talk today is about a very simple idea. I want to talk about epochs. This seems like a very basic idea in machine learning. We often just train the model on the same data multiple times. However, this seems to have become a kind of like bad word in the large language model training literature. If you read the GPT-3 paper, they very clearly say that data are sampled without replacement during training. Now, they do repeat some specific sources, like Wikipedia, but they make very clear choices about what they repeat, and they avoid it when they don't need to. In the POM paper, they say we train all three models on exactly one epoch of the data and choose the mixing portion to avoid repeating data in any subcomponent. Now, I think these kind of papers kind of made people think that something will really go wrong if we repeat the data multiple times. But if we're in some sense running low on data, it seems like a natural thing to do. So in this paper, we wanted to explore what happens if you repeat data and just kind of make empirical observations of the scaling law under this regime.
Good question.
Yeah.
But in the chinchilla paper, they were not using one epoch.
They were. They never repeat the data.
I see, they didn't.
Yeah.
Oh, I'm thinking of a different.
Yeah. Okay. So we're going to do the following. We're going to run very controlled experiments on a very large scale. So we had access to a large supercomputer, and we're able to run many different large language models. For this paper, we ran 300 training of large language models, and we run under the following settings. So we're going to vary the model size from 2.8 billion parameters to 8.7 billion parameters. The training data here represents the chinchilla optimal number of tokens for those model sizes. And on the left, you see the amount of compute. So a large amount of compute, but not really out to the scale of what we're seeing of giant large language models at the moment. For each of these, we're going to train 8 different models, and we're going to vary the amount of data that is repeated. So we're going to basically subsample the data and run multiple epochs over the same tokens. All the other details are in the paper, but the key things to note are that they're all using a standard architecture. They're all using standard hyperparameters, basically adapted from the chinchilla paper. And I'm going to show experiments mostly on the C4 dataset, which is a relatively clean dataset of web crawl data. We also have other experiments in the paper with other datasets. Okay. So just to give you a sense of the data setting, when I say epoch, I don't mean multiple epochs on the same amount of unique tokens. I mean keeping flops fixed. How can we split the data such that it is computed with multiple epochs? So when I say 7 epochs, that means the same number of flops as 1 epoch, but just that I cut off the amount of unique data earlier and then repeat it. This is a point of confusion, so I just want to make sure it's clear exactly what I'm doing. So all these models will be run for exactly the same number of flops, but I'm changing the amount of unique data. So here are the conclusions. So 3 different runs with different parameters. Within each one of these columns, everything is the same number of flops. When you train with different number of parameters on one epoch, so all unique data, you get the following loss curves. This is validation loss on the left, number of training tokens on the bottom, and final loss at the final point. So as might be expected, for chinchilla compute optimal models, going from 2.8 billion parameters to 8.7 billion parameters leads to a relatively large increase in accuracy or a decrease in loss. So we go from 2.6 to 2.4. Now I run the same size models, but 2 epochs. So that means I only had half as many unique tokens, but I ran through them twice. You see very similar curves. Now I do 3 epochs and 4 epochs. So at 4 epochs, I only had 25% of the unique tokens. But if I use the same amount of flops, I get roughly the same amount of loss, the same value of loss. When I get up to about 7, there is a kind of noticeable gap here. And when I get to about 14, the loss kind of tails off much earlier. If I keep on going up to 44, I start seeing kind of instability or overfitting, or kind of go outside the regime itself. So main conclusion is similar performance for a few amount of repeats. And when you go out of scope, you get bad performance. Yeah.
Is there a way to quantify this in terms of, say, like the effective amount of data you have if you're doing, say, 2 or 3 epochs? Right? I guess it's like a little bit hard to eyeball, but maybe it looks like for 3 epochs, it's sort of as if I had maybe like 42 billion tokens instead of 55 billion.
This is a great idea, Jacob. We really should do this. Give me 2 slides.
Okay, great.
Cool. But yeah, I think you get where we're going. Yeah.
Another question was, I mean, I've seen some of these before in some other shows, but
do you see any kind of overfitting in terms of train versus validation?
Yeah, so this is validation loss. I think this is definitely, what's up?
But the gap between training and validation.
Oh, great question. It's really interesting actually, because people normally run 1 epoch. I don't think of that difference for language models, but you're right. Here, that should matter. I don't remember if those numbers are in the paper or not, but we should have included those because they matter a lot more here. But I don't know offhand. I mean, you really would expect that since you're seeing 44 epochs. You'd think the train loss would be really, really low, right?
And maybe another related question was, did you check on the downstream evaluations if they behave?
That is coming, but yes, they do behave as you might expect. Yeah.
So for these like 44 epochs results, you see these kind of classic overfitting curves where you get this sort of catastrophic failure. Mm-hmm. I'm curious, I kind of wish these curves ran out for longer, because I'm curious if these, when you have more data, it's not clear that you're going to see the same catastrophic overfitting behavior. Do you think that if you just run these curves out for many, many more iterations, you see the same overfitting with the larger data sets as well? Or if you, like, eventually you get a critical mass of data where you become somewhat stable over different model sizes?
Well, just to be clear, though, we want to be really careful. So there's actually less unique data here for 44, yes. Right? So there's more tokens, but less unique tokens.
Yes.
So there are some numbers we'll get to that kind of answer some of the questions you're asking. But I do want to note that in this work, we're less concerned about the kind of overfitting case, because we didn't really try to make this work. We just used roughly the same hyperparameters. What I'm really interested in is kind of this regime here, and kind of quantifying what happens in this space. Cool. So this phenomenon holds in other data sets. It's not unique to C4. We see a similar curve. Now, again, I don't want to make any point that this is like a deep thought, right? What we're seeing here looks like what you might imagine from kind of training with a kind of standard machine learning system. We're just kind of validating this for large language models and trying to quantify it. Cool. Okay. So getting to the question Jacob asked, I think the next natural thought is, how do we quantify the effective amount of data that we have when repeating? So this really matters because when kind of deciding how to allocate our flops, we know what to do if we have infinite unique data, but we have to decide what we're going to do in the case where we have a constrained amount of data to work with. So we're going to use a relatively simple model, which is we're going to think about data having exponential decay. So the analogy here is to something like a half-life, where every time we use the data, it decays in some exponential form. We have some term delta that's going to correspond to the decay of the data on repeated use. So just to kind of make this a little bit more tangible, the model is that we're going to have this new term, which we call d prime. The d prime represents the effective amount of data that we're actually utilizing under repeat. And that's going to differ from the unique data u, which is the actual data we were able to collect. We're going to have another term rd, which represents the number of repetitions of the data itself. So just to make this a little bit more tangible, if delta was equal to 1, it would mean that we wouldn't have to worry about this problem at all. The opposite. If delta is equal to 1, then we wouldn't be able to repeat the data at all. It would use all of its value on the first use. If delta is equal to 0, then we can repeat the data forever. And it's effectively the perfect world where we don't have a problem at all. And if delta is equal to 0.5, then repeated data retains 50% of its value. To simplify things, we're going to think about things in a compounding form. So when we write out the equation, we're going to use this form instead, where instead of measuring delta, we're going to have a term which we call r star d. And that's going to correspond to the number of times we can repeat the data before we get a catastrophic failure, for basically it gets very bad. So if r star is equal to 0, that's the case where repeated data is worth nothing. If r star is equal to infinity, repeated data is as good as new. And as we saw from the previous experiments, the r stars kind of somewhere less than 44 for our underlying language modeling data. Great. So now let's look a little bit about how we fit these terms in practice. Yeah, go for it.
Can you go back to the functional form there?
Yeah.
Wait, so if r star d is infinity, isn't this saying you get infinite data even when rd is finite? Or I think I maybe just not parsing this correctly.
No, that's right. So it's I think r star d is roughly the same as if delta was equal to 0.
But like, say like rd is like 2, so I've only repeated the data twice. Then it seems like d prime should only be like 2 times u, even in the best case. But this is saying it would be like infinity times u.
I see.
Like I'm wondering if that should, maybe that the first r star should be just rd.
Good question. I don't think I'm going to be able to do this on the fly,
okay,
but I will look in and make sure I don't have a typo or anything. Okay. Yeah.
Do we ever change the learning rate because we are repeating the data? Like for example, like maybe I repeat the same data twice, but I use half the learning rate. Like exactly the same result as if I trained the data once with twice the learning rate.
Yeah, it's a good question. So we mostly just stuck with the kind of chinchilla or an adapted version of the chinchilla formula for these terms. The chinchilla learning rate's a little bit complex. So the details of exactly how that works are important. But at this scale, we weren't really able to experiment too much with kind of different learning rates or things of that form.
So it is possible that the optimal hyperparameters for training the model actually change when we are working with repeated data compared to regular.
I think that's possible. Yeah, I would love for someone to explore that more. Okay, so I think this slide gives us a sense of the final return. So what I'm going to do here is I'm going to plot the final point of the previous experiments. So this is exactly the same data that we saw before, just shown in a different form. So each of these points represents a different version of the model trained with a different percentage of unique tokens. The kind of line here represents the kind of perfect world where everything was the same, just based on the parameters and the flops. And the line on the top represents a kind of strong form of decay. Each of the points that we show here represent our empirical experiments. And the line represents the kind of predicted version of this under the decay equation I showed you on the previous slide. Here's a version for a larger model. So this is with 4.2 billion parameters. And here it is with 8.7 billion parameters. So for all three of these, we see a relatively good fit for using a kind of exponential decay of the data itself. We can also look at the predicted loss for a different number of epochs in practice. So for a model of 2.8 billion parameters, the line, the dotted line, represents what you'd expect from using unique data to get our new tokens. And the predicted line represents what we expect from repeating the same data starting from just around 100 billion tokens. So we see that around at 4 epochs, things are relatively close to having unique tokens. But as we get out to more and more epochs, the kind of marginal value of more repeats becomes relatively low, particularly when you consider the additional flops required to utilize them. Here's the curve for 4.2 billion and for 8.7 billion. Great. Okay, so now let's go just through what this means for the chinchilla formula itself. So at this point, you probably can guess what we're going to do in terms of kind of predicting those lines from the previous slide. We're going to take D, and we're going to instead put in the effective amount of data D prime that we think will happen under the decay of using repeats. So we just substitute in our D prime formula from the previous slide to get that part of the equation. We also found that it was necessary to substitute in for n to take into account the fact that the parameters are being learned from less effective data. So we have a similar exponential decay here on the parameters itself. We have a min here to represent the value we get from the unique number of parameters, the unique tokens learning those parameters. Yeah.
Is this something empirically derived or theory? I mean, not clear to me that this should happen. There's some effect, but the precise functional form.
So we took basically the same functional form.
Yes.
I agree that I don't fully understand the kind of causal reason here. I think the theory was something like the feature learning that goes on in the first term will be weaker because of repeating the data. But beyond that, this is just a kind of empirical.
But I guess, yeah, the question is, it fits.
This fits, yes.
Oh, that's interesting.
Yeah.
So what are the free parameters? Like just R star and R star and an R star?
Yeah, it's a good question, actually. So we fit A, B, alpha, beta, and E with the same way that they did in chinchilla.
And that's, you just use the one epoch results to fit those?
Exactly, yeah.
And then once you add in the multi-epoch, the only new parameters are R star and R star D.
That's right. Yeah. Cool. Any other questions? These are great questions. Yeah.
So the idea here is if you can repeat it 10 times or so, without much loss. Now, if you were to change your hyperparameter on, I call it the gain of the gradient descent, I don't know what it's called. But if you were to change that, for a little bit more feedback, then would it saturate at a lower number? Are those numbers related?
I love that people are asking this question. I don't have a good answer for it. If it motivates work in this area, it would be awesome. These experiments are large enough that we really just took what they said in chinchilla, adapted it to our data, and ran it to scale.
But could you change that hyperparameter and see what happened? Is that a doable experiment?
With enough compute, one could do that. Yeah, absolutely. And I should mention that in the Chinchilla paper, they do change the hyperparameter setting from previous large language models, and they do find that makes a difference. So I don't want to say that these are kind of universal properties of the universe. They're more kind of just empirical tools. Yeah.
Yeah, related question. So yeah, in the Chinchilla paper, they were more methodical with hyperparameters, plotted out the curves and take the minimum. You're just staying with the minimum. You're not doing that search again.
That's right. That's right.
So there might be something to squeeze out there.
Yeah, absolutely. It's a really good point. Again, I just want to note that it's hard to do these things simply because the economics of running these is very tough. Yeah.
Eventually, you're limited by the compute taken to do these large language models, but so a lot of these results, it seems like perhaps they might apply to smaller models as well. Have you done any experiments?
Yeah, we haven't tried to scale it down as far as I know. Yeah. Cool. Yeah.
Sorry, I just missed the rationale for the.
Yeah, so the rationale is that the n prime term represents how kind of good the model could be in these settings, and that we think in a kind of feature learning style model, the repeats of data is going to kind of limit what could be learned here. I know that's not super satisfying, so I think maybe the other argument is it's a kind of empirical question, that if you think the first term would maybe stay exactly the same, then the R star value should maybe reflect that. Okay, great. Okay, so I have a couple more interesting results I want to show, and then we can talk about some of the questions about data constraints. So we did this, we get values for R star D and R star N. That's what I showed you on the previous slide. Okay, next I want to talk about this question of allocation. So a practical question you might have is how to decide how often you should repeat and how big your model should be. So given the Chinchilla curve, if we're going to repeat data because it's limited, what actually happens to the curve itself? Do we want to repeat more often, or do we want to add more parameters? I must say, this was not intuitive to me of which choice you might make. If I only have, say, 100 billion tokens, I actually wasn't sure what I should do in practice. So what we did is we kind of plot this data. This is with 100 million unique tokens, varying the model size and data repetitions. So every point on this graph represents a different choice of repetitions versus model parameters given 100 million unique tokens. The colors of the point represent the final loss, and the contour plot represents where the loss was kind of minimal for these models. So recall that the amount of flops is multiplicative, so either going to the right or up will cost us more flops in practice. This black star here represents the kind of only using unique tokens Chinchilla point, whereas this white star here represents a good loss on the model itself. So when you fit the curve or the formula we saw on the previous slide to this data, you get contours of the following form. So it basically shows that as you add more flops, you get better, but it also shows the kind of ratio of adding more parameters versus repeating the data more times. And in particular, if we draw the Chinchilla curves over this data, we can see that equal scaling gives us something like this, but our formula predicts that we should roughly be repeating the data more often before adding more parameters to the underlying system. So we actually start getting a better loss about here, and kind of scales below the Chinchilla line. Unlike Chinchilla, where you can keep on going ad infinitum, for our curve, it kind of peaks out at a given point, and this corresponds to the point where our hyperparameters seem wrong, and we leave outside the regime and kind of go into overfitting mode, or whatever you want to call that. Cool. So just to summarize, this is a hypothetical Chinchilla line. Our contours predict that we should scale the repetitions faster than we scale the number of parameters. And this corresponds to the fact that our R star D value is higher than our R star N. Any questions about these results?
So I just realized now that the term, the term by the model, the R there is different than the R for the data.
That's right. Yes, they're learned separately.
Because it didn't make sense for one.
I see. I see. Yeah, sorry. Yeah, we gave them similar names because they're kind of analogous terms. Yeah. Yeah.
Have you looked at kind of extrapolation experiments with these fitting experiments? So fit on small scale in your regime and evaluate how good the fit is on a larger scale?
Yeah. We tried some extrapolation experiments where we fit these curves on the small scale and tried extrapolating to a larger scale. So for these, we start with 25 billion tokens as our data constraint, and we run 2 larger models. So these 2 models have the same number of flops, but one of them utilizes a kind of naive adaptation of the chinchilla formula, whereas the other kind of slopes downward, utilizing the data scaling law that we predict. What we find is that for the same amount of flops, we see that this model gives us a better loss. This looks small, but it's relatively large at this sort of low loss for these models. And I think this is kind of as expected from the kind of smaller results, that repeating the data a bit more often and using fewer parameters seems to give a better loss in practice here. Cool. And again, I don't really want to claim any kind of mechanistic reason why this happens. This is kind of mostly an extrapolation experiment, as Jonathan noted, utilizing our small experiments to try to scale this in practice. Cool. One really neat consequence of this is that we're able to go back and kind of counterfactually examine previous papers. There is one large language model that seemingly repeated data, and that was because the kind of data scale was already exhausted. So this work on Galactica was particularly trained on scientific papers. And when you train on scientific papers, there's just a limited amount of them. And so they decided at this point here to repeat the data 4.25 times. But note that what they decided to do was actually to add more parameters in order to repeat less. So they went above the chinchilla curve. So I think what we're arguing is that they may have been able to go below the chinchilla curve and had a better loss. They additionally trained a much larger model and repeated 4.25 times. And in this point, we think they could have done even better by repeating something like 12 times with a much smaller model. So I think this is, it remains to be seen whether this is true in practice, but we think the kind of predicted values from this experiment may have actually helped to kind of produce a better large language model. Great. Okay, so I do want to leave time for questions. I'm going to do about 2 minutes more on some of the other experiments in the paper. So in some sense, I think these results are nice in that they give us an empirical thing we can do in the next couple of years to get extra orders of magnitude. But they're also kind of pessimistic in that they say, well, this maybe only lets us double 1 more time or 2 more times. So we wanted to look at other complementary strategies that might be useful in practice. So we looked at a couple in the paper. One is to utilize code data to try to fill out to get extra tokens. And the other is to revise the filtering process of large language models. Now, the second one gets into some of the specifics of how these models are trained. So I don't want to go into that too much, or we just don't have time to go into the details. But roughly, it's going to alter the way that these data sets are constructed in order to get more effective tokens, or to get less effective tokens and repeat them more often. I think this code one is actually a little bit more interesting in practice.
Question?
Yeah.
So that's a one-time thing, or you are adjusting along the way?
Can you say that one more time?
That you're looking at the perplexity filter to adjust.
One-time thing.
One time.
Yeah. So we're gonna remove the default perplexity filter for these data sets, put on, say, a higher perplexity filter, so get like more high quality data and repeat it more often. Something like that.
So like a weaker model that's giving you a perplexity.
Oh, yeah, assume we have a magical perplexity model that we get to start with. Yeah.
Which is more powerful or less powerful?
I actually don't know in practice. Let's say more powerful, just for a second.
Do you consider diversity in the data collection?
Really good question. Some of the experiments do deduplication, which I guess is a very weak form of diversity. Otherwise, we're just using default kind of common crawl processes. So we kind of take however they decided to construct the data set. Okay, so I think this is my last kind of experimental slide. There's a lot of variance here because these are actually run not on loss, but on a collection of basically benchmark data sets. These benchmark data sets they're kind of NLP data sets, but you should be aware that a lot of NLP data sets kind of look like reasoning sort of tasks. So they include lots of underlying skills. The purple line here represents the repeating data curves we've roughly seen so far. So instead of showing perplexity, this shows downstream accuracy, but the graph looks pretty similar as what we've seen. So this is with full unique data, this is with repeat, this is with repeat, and then this is like lots of repeat, and then it tails off. The main point we wanted to make here is that code seems to work quite well, that we can maintain pretty high accuracy by replacing a large number of tokens with code. It seems to basically keep similar curves as repeating data. And in fact, for some of the tasks, it seems to help a lot. But there does seem to be evidence that kind of filling up half of the remaining tokens with code is pretty useful for improving these systems. We have some experiments on perplexity filtering and deduplication in the paper. I don't want to draw too many conclusions from these now because some of the details are important to understand them. But we find that this is pretty data set specific, but that it seems like things like filtering with perplexity and then repeating can be effective and should be explored in future work. Great.
Quick question about the code. Are any of these downstream performance, the downstream task involve code style understanding, or is it just that somehow code happens to have natural language in it because people write lots of comment, or do you have any insights?
Yeah, I have lots of thoughts. None of them involve code. I don't think code has that much natural language, but a lot of the tasks to me feel like basically code tasks. So a bunch of the tasks are like these like kind of like baby or something, like these like tasks that are expressed in natural language, but really they're about kind of matching two things and putting them in. So to me, they feel not so different than synthetic tasks or code tasks. If that makes sense.
So that's the task on which you're seeing improvement.
Yeah.
Like baby.
Like baby, yeah. Which, despite being, I am an author on that paper and I am not super proud of it, but yeah, it is like a weird task in that way. Yeah. Yeah, actually, give me 1 millisecond. I just want to conclude. So this is kind of the main conclusion from the talk. And then the last thing I'll mention is that people have been using this on downstream tasks. So we actually, the authors of this paper were able to train a Finnish language model. They repeated it 8 times, and they see kind of actual use from this in practice. So it's still not massive number of tokens, but you do get a practical amount of effective tokens in practice. That all being said, I think there was lots of really great conversation about this yesterday, and I don't want to make any claim that I think we're inherently like screwed. I think there's lots of other orthogonal ways that we might be able to get more data tokens. But I do want to note that like a lot of the progress so far has come from just scaling the same transformer model. And I do think it is interesting that maybe that is like kind of getting near some kind of endpoint. And so hopefully works like this encourage people to try more creative ways to get value out of data, to get value out of other modalities, and to kind of come up with evaluations that are better than these kind of just asymptotic evaluations. So why don't I end there, and then we'll take some more questions. Yeah.
Is code special, or is one way to make progress on Finnish, even if the Finns don't like it, to augment the Finnish data by 2 times as much English data?
Yeah. It certainly is worth trying. I'm not 100% sure that the reasons people want to train language models in one language are entirely like perplexity based. Like there may be other reasons why people want to train language models just in one language, but I agree that if we're just caring about perplexity, it does seem like multilingual models are a more effective way of doing it.
You say, I don't understand really precisely what you mean by training off code. Are you taking the raw Python code or is it filtered some way?
Raw Python code.
So that means it must get really good with if and then and for keywords when you're training off all that code.
I think the lexical things are trivial. It gets that right away. I think it's probably learning all sorts of things like copying long distance relationships or kind of basic mathematical reasoning.
But what that has that have to do with like natural language?
Yeah, I think that's what I was saying earlier, is that we're not measuring natural language perplexity. We're measuring accuracy on tasks that NLP researchers came up with. And some of those have properties that require similar skills as code, is my theory. Yeah.
All right, so when you're repeating the data, is this just a matter of like multiple epochs, the model hasn't converged in some sense? And that by repeating the data, you're just getting close, you're doing less early stopping in some ways?
Yeah, I think that's a fair point. I think the reason I didn't use language like convergence is because when talking about scaling laws, you're actively considering the number of flops. And I feel like that feels slightly different. So we're interested not just in convergence, but in like the actual cost of running it. Right. So we're getting more value in some sense out of the repeat. Yeah.
Right. I'm just wondering, because running multiple epochs, it sort of convolves the regularization you get from early stopping with the amount of data. But also I have a more general question here, which is why not subsample the data in each epoch rather than subsampling once and then repeating?
Because we're literally assuming that you just do not have more data.
Oh, okay.
Yeah, like the setting we care about is like, yeah. This all being said, people in this room can tell me more, but I don't know how to think about what regularization means when you have 500 billion parameters, right? My terminology may be out of date in that regard.
Going back to the code questions, I might have missed it, but you were focusing on the fact that the tasks are somehow code-like. Are you saying that if you were to look at perplexity, you don't see the same results?
Yeah, certainly if you train on half code, your perplexity on language doesn't go down in the same way. But that makes sense to me because it's out of distribution. Yeah.
But does it go down?
That's a good question. I think there are results in the paper.
I don't need epsilon, but
yeah. I actually don't know offhand. Yeah.
Yeah, can I think of these results as a kind of certificate on the inefficiency of SGD as a learning algorithm? Like, you have to look sometimes to get the result.
Yeah, but I mean, we didn't invent that, right? People have like that's certainly known.
Sure,
Yeah,
but maybe it suggests that there's room for improvement.
fair enough. Although, I mean, man, like SGD has survived a lot of attempts to dethrone it. So, yeah.
I mean, it's also worth mentioning that CFAR10 models are trained for like 3,000, and so like this is, in terms of inefficiency of SGD, is incredibly mild, right? But yeah.
Yeah, and I think when we talk about efficiency, we should talk about flop efficiency as well. So like you come up with a crazier method, but it might require more flops in some way. Yeah.
When you're getting like smaller data sets, are you just randomly sampling them from the larger one?
It's exactly this.
So like for the 7 epochs, like are you just taking like 1/7 like random sample? So would
No, it's the same. We just cut it like this.
Oh, like you just take like the first 7th and then
we like shuffle once and then cut.
So like the diversity of like the smaller, like if I were to just have a smaller data set, like in this the diversity comes from a larger data set, right?
Oh, that's a good point. Yes, we don't make any claim about like if you had a smaller data set and it was all in one domain, what would happen? Yeah, it really is assuming sample. Dee, did you have a question? Do you want to talk about some of the bigger stuff?
Oh, not bigger.
Okay.
So I'm curious about the perplexity filter, because this seems to be very like a strategic choice for people training large language models. Like yesterday, the GPT-4 talk was talking about they only use top 20% somehow. If it's very sensitive, I guess, how does it play a role in this process? What has been filtered out? If the filter optimize perplexity, then our pre-training also optimize perplexity. Is that a problem or issue?
That's a really good point, and I think it relates to some of the conversations yesterday about like implicit distillation, that you might be getting benefits from having like higher quality data. Whereas we also, Dee and I were talking about how some of these perplexity filters may filter out dialects or kind of, I don't know, parts of the distribution you really care about a lot a priori before training. That being said, I think, Colin, maybe you can answer this slightly better. Do you have a sense of like how people should think about perplexity filters in practice?
Well, I mean, I don't want to zoom out too much, but I think it just kind of ties into the question of like what high quality data is, because any discussion of how much data is available implicitly assumes that there's some good data and some bad data, right? Because there are web pages that get filtered out when you're creating a data set that are just like random characters. And we would all say that's bad, that's low quality data, but if we don't, then our data set is larger. And like, so you can't have a discussion about how much data do we have without defining what high quality is, but you can't define what high quality is. It's an incredibly nebulous concept.
It's a hard concept, yeah.
Yeah, and like perplexity filtering for sure is not a proxy for high quality. Exactly, but I don't. Maybe it's reasonable. I mean, I think like I also think it's a question of diminishing returns. Like again, if you just look at the data that you've scraped, some of it is garbage. You come up with some heuristics to get rid of the garbage. That gets rid of a bunch of clearly garbage data. But then as you add more heuristics, you start to filter up stuff that's not actually garbage. And perplexity filtering, I think, is far enough down the chain of filtering that that we can't be confident anymore that it's doing what we want it to do.
And sorry, is Nicholas Carlini here? I think I saw him yesterday. I think he has other views on this as well. Well, if you're interested in this topic, he also has written a lot about this. Yeah.
Oh yeah, sure. So, when you say that you're not working, on actual natural language processing computation, can I ask more like a question about the motivation? And this is really, I guess, motivated from, a quirk of making that ChatGPT 3 comment about sampling without replacement, which to me infers that it's a hypergeometric distribution. So like, and when you imply that you're using something like a half-life decay, and this is more like a Poissonian distribution, I'm a little curious then, should we expect to see more Poissonian-like distribution features in what you're doing and not hypergeometric distribution features?
Yeah, let's see. I wasn't really making any, I hear what you're saying. I wasn't making that claim. I think I was making a much weaker claim of just that like they were trying not to literally repeat as opposed to, because I don't think they're doing anything like interestingly hypergeometric. I think they're just literally just not, they're just saying like, we have so much data, why don't we use it all? And that will be the most effective way of going about the process.
So we should probably break here. So let's thank Sasha again. So there should be, I think, refreshments outside. We'll reconvene in 20 minutes.